Right now, at this very moment, Earth sits in the crosshairs of something most people will never see coming. A stream of charged particles racing toward us at 700,000 kilometers per hour is about to slam into the invisible magnetic shield that wraps around our planet. This isn't just another solar storm. This is what scientists quietly call a perfect coupling event. And it's happening at the exact moment that an interstellar comet, the third ever confirmed from beyond our solar system, has vanished behind the sun without explanation. Some experts insist these events are unrelated, mere coincidences in a vast and chaotic universe. Others aren't so sure. Because while this cosmic drama unfolds overhead, seismographs across the Pacific Rim have registered a sudden cluster of powerful earthquakes, and the timing raises questions that make even skeptical scientists pause before dismissing the pattern outright. The sun doesn't have a hole in it, not really, but what astronomers call a coronal hole might as well be a gateway to understanding how profoundly connected we are to the star that gives us life. Imagine the sun's surface as a bubbling cauldron where magnetic field lines normally loop back on themselves, trapping superheated plasma in tight, controlled arcs. Now imagine a region where those magnetic shackles suddenly release, where the field lines stretch outward into space like gates left wide open. That's a coronal hole. And when one of these regions spans across the sun's equator, bridging north and south hemispheres, it becomes a cosmic highway for solar wind to escape at velocities that can overwhelm planetary defenses. The October 2025 event revealed exactly this configuration through imaging from the Solar Dynamics Observatory, capturing an unusually broad unipolar coronal hole with negative polarity stretching across hemispheres. What makes this particular moment extraordinary isn't just the size of the opening or the speed of the wind, it's the precision of the aim. Earth sits directly in the path, and the magnetic door between our world and the sun's fury stands open wider than it has in months. When that 700 km/s stream of solar wind arrives at Earth's doorstep, the real contest begins at a boundary most people never think about, the magnetopause, where our planet's magnetic field meets the incoming barrage. This isn't a gentle interaction. The interplanetary magnetic field embedded in the solar wind acts as a key that can either unlock or reinforce Earth's defenses, and everything depends on which direction that field points. During the October event, the interplanetary field swung sharply southward, holding near -12 nanotesla. And that orientation matters because Earth's own field points north. When these opposing fields collide, they don't bounce off each other like repelling magnets. Instead, they snap together in a process called magnetic reconnection, essentially opening a channel for solar energy to pour directly into the magnetosphere. The consequences cascade through our technological infrastructure. Power grids experience fluctuations as invisible currents surge through transmission lines. Satellites feel increased drag as the upper atmosphere heats and expands. And most visibly, auroras erupt across skies far from their usual polar homes. On the night of October 12th, shimmering curtains of green and crimson light danced over Michigan and Maine, a stunning reminder that we live inside a magnetic bubble that's constantly under siege. Every spike in solar wind velocity, every shift in field polarity sends ripples through the global electrical environment. And while most of these effects remain invisible to the average person going about their day, they reveal just how thin the barrier between cosmic forces and everyday life really is. But there's another visitor in this story, one that doesn't belong to our solar system at all. Comet 3I-ATS arrived from interstellar space, carrying chemistry that reads like a message written in an alien language. Most comets we've studied are dominated by water ice, the frozen remnants of our solar system's birth. But this interloper is different in ways that challenge everything astronomers thought they understood about how planetary systems form. Its coma, the cloud of gas and dust surrounding the nucleus, is fueled primarily by carbon dioxide outgassing at rates nearly 8 times higher than water vapor. That's a chemical signature more typical of objects formed in the frozen darkness beyond Neptune than anything native to the inner solar system. And it suggests this comet condensed in a stellar nursery with conditions radically different from our own. Spectroscopic analysis reveals a nucleus smaller than a kilometer across, yet active enough to shed up to 4 kilograms of material per second, even at distances of 4 or 5 astronomical units from the Sun. The dust it releases favors large, heavy particles, instead of the fine grains that create the spectacular tails we associate with great comets, resulting in a faint, asymmetric haze that defies typical expectations. Its rotation period of just over 16 hours matches the tumbling motion of other active comets, but the organic-rich surface chemistry, with that extraordinary carbon dioxide to water ratio, set it apart as something genuinely foreign. As one mission scientist put it, this is a messenger from another star system, carrying a recipe we've never tasted. And as it rounds perihelion, the closest point in its journey past our Sun, the intense solar radiation will test that alien chemistry in ways that might reveal secrets about planetary formation across the galaxy. Then, in late September, as the solar wind battered Earth and 3I Atlas approached the Sun, seismographs lit up with a cluster of magnitude 7 earthquakes that sent shockwaves through both the planet and online speculation. The timing seemed too perfect to ignore, the Sun erupting, an interstellar visitor disappearing behind our star, and Earth's crust fracturing in multiple locations within days of each other. Social media exploded with theories connecting these dots, some suggesting the solar outburst triggered the quakes, others claiming the comet's passage somehow destabilized our planet's interior. But when you examine the data against historical baselines, the picture becomes more complicated and less sensational. According to NOAA's Space Weather Prediction Center, Earth experiences approximately 15 magnitude 7 or higher earthquakes every year, distributed roughly randomly across the globe. This week's seismic activity, while dramatic and devastating for those caught in it, falls comfortably within statistical expectations and shows no anomalous pattern when compared to decades of records. No mainstream seismologist accepts a direct physical mechanism linking solar wind to tectonic plate movements because the energy scales simply don't match. The forces required to shift continental plates dwarf anything the magnetosphere could transmit downward. Meta-analyses of decades of earthquake data find no reliable correlation between solar storms and seismic timing, no matter how compelling individual coincidences might appear. Still, speculation persists in certain corners, invoking unproven mechanisms like ionospheric coupling or subtle changes in Earth's rotation, but these remain outside accepted geophysics precisely because they lack reproducible evidence. As one NOAA forecaster explains, the burden of proof lies with those claiming a connection, and extraordinary claims require extraordinary evidence, not just dramatic timing. Yet the debate itself reveals something important about how we process unlikely coincidences and search for patterns in chaos, and it underscores the challenge of separating genuine scientific signal from the noise of random occurrence. Right now, behind the Sun, where no telescope on Earth can see, 3I Atlas is either surviving its closest approach to our star or being torn apart by forces that would vaporize most comets we've ever observed. 4 distinct fates wait on the far side, each leaving its own signature in the data that will emerge when the comet moves back into view. The first possibility, the least dramatic but most expected, is intact survival. The comet reappears with brightness following predicted curves, its coma remaining compact and stable with no sudden changes rippling through its light. This would confirm that despite its alien chemistry, 3I Atlas can withstand the same thermal and gravitational stresses that native solar system comets endure. The second scenario involves fragmentation, where the nucleus splits under stress, and this outcome would announce itself immediately in spacecraft imagery.
Coronagraphs aboard SOHO, Stellio, and the Parker Solar Probe would catch a sudden brightness spike, often exceeding a full magnitude, and instead of a single point of light, images would reveal a train of fragments stretching along the comet's orbital path. The coma would expand chaotically, the tail might split or develop kinks, and in some cases, a rare sodium tail, bright yellow and distinctive, could flare up as sodium atoms liberated from the fragmenting nucleus catch sunlight. Past comets like Lovejoy and Ison showed exactly these signs before their final moments. A third possibility is dormancy, where the comet emerges but its activity has collapsed entirely. The coma shrinks, the tail fades, and the nucleus appears almost stellar, faint, unresolved, and potentially lost in solar glare. Ground-based telescopes might struggle to recover the object at all, with only sharp-eyed mission scientists flagging the anomaly in archived data. The final and most dramatic fate is total disintegration, where the comet simply fails to reappear, leaving no trace in coronagraphs, no fragments, no outburst, just a silent gap where something should be, and perhaps only a ghostly dust trail or a brief unanticipated brightness spike marking the moment of its destruction.
The wait for answers transforms into a global detective story as observers prepare for recovery operations. It begins with a single image uploaded to SOHO's Quick Look archive every 12 minutes, each frame scrutinized by comet hunters worldwide for any sign of 3I ATLS, a faint point of light, a sudden brightening, a subtle distortion in the solar background. When something unusual appears, an unexpected spike, a new fragment, a sodium flare, alerts ripple through the observing community within minutes. Robotic telescopes take over next, with facilities like the Zwicky Transient Facility and Pan-STARRS programmed to sweep the region as soon as the comet moves far enough from the sun's glare. These automated surveys cover enormous swaths of sky in single exposures, comparing fresh images against star catalogs and flagging anything that shifts position or changes brightness. Photometry protocols measure light in multiple filters, logging magnitude and color in real time, and the pattern of these measurements tells the story. A steady, predictable rise suggests an intact comet, while a sudden jump points to fragmentation or outburst. Amateur astronomers play a critical role in this relay, their backyard telescopes adding redundancy and extending searches into gaps between professional surveys. Every successful sighting, logged with precise coordinates and brightness, builds a chain of evidence tracking the comet's recovery. And this coordinated approach, spacecraft triggers feeding into robotic sweeps, supported by human vigilance, forms the backbone of post-conjunction searches. While the world waits for 3I ATLS to reappear, another cosmic visitor offers a more immediate opportunity for anyone willing to step outside before dawn. Comet Lemon now glides through the constellation Cancer, rising in the east an hour or two before sunrise and presenting a rare chance for observers with simple binoculars to catch a living piece of the solar system in motion. No telescope required, no special equipment, just clear skies, patience, and the willingness to set an alarm for the quiet hours before the world wakes. At magnitude 4 to 5, Lemon appears as a fuzzy, diffuse patch against the stars, bright enough to stand out through binoculars, but subtle enough that you need to know where to look. Under dark skies, the coma resolves as a soft, round cloud with a hint of tail stretching away from the sun, spanning perhaps half a degree and often lost in morning twilight, but binoculars reveal its subtle glow. The next 2 weeks represent peak viewing as the comet climbs higher each morning and the moon stays out of the way. And by mid-November, it will fade and slip closer to solar glare, making this window the best chance for first-time comet observers to connect with something genuinely ancient and exotic. Any binocular works, even basic 7x50 or 10x50 models, the same you'd take to a baseball game, and even in suburban skies, the comet appears if you know exactly where to point. Many observers keep star charts handy or use phone apps to pinpoint position, setting alarms for 4:30 in the morning, grabbing thermoses, and stepping into backyards before dawn light erases the stars.
For those who catch Lemon, it becomes more than a smudge of light. It's a practice run for bigger cosmic events ahead.
a way to tune eyes to faint details, learn the rhythm of the sky, and join a community that chases these fleeting visitors across the heavens. Every observation, whether a quick glance or a carefully logged brightness estimate, adds to the global record and builds skills that matter when the next comet or interstellar object appears. Looking beyond this moment, another visitor, Comet Swan, draws attention for its unusual ultraviolet signature, a hydrogen corona invisible to human eyes but blazing in ultraviolet wavelengths that acts as a signpost for cometary chemistry. Expected to reach binocular visibility in early 2026, Swan offers researchers a comparison case for understanding how different comets respond to solar heating, and by comparing light curves of Swan and Lemon, how each brightens and fades over time, scientists can tease out hidden physics governing outgassing, fragmentation, and the slow erosion of icy bodies under stellar radiation. But the cosmic calendar extends far beyond these near-term events, revealing a timeline of encounters that frame our place in a restless solar system. 5 milestone dates now stand out as waypoints for anyone tracking this ongoing story. Late October through early November 2025 marks the recovery window when telescopes worldwide hunt for 3II Atlas returning from behind the Sun, and what we find or don't find will rewrite assumptions about interstellar comet survival. On April 13, 2029, asteroid Apophis passes so close to Earth it will dip below geostationary satellite orbits within 32,000 kilometers, visible to the naked eye over parts of Europe and Asia in a flyby that offers unprecedented opportunity to study a near-Earth object. September 20th, 2040 brings a planetary alignment where Mercury, Venus, Mars, Jupiter, and Saturn cluster on one side of the Sun, offering a rare tableau for astronomers and skywatchers, though the actual gravitational effects remain negligible despite persistent online claims. Looking farther out, the year 2060 carries speculative promise of a megacomet, flagged in current surveys as a distant, slow-moving object with potential to rival great comets of the past if brightness predictions hold. And in 2177, Pluto completes its first full orbit since discovery in 1930, a slow, stately lap that frames the entire modern era of planetary science and reminds us that some cosmic cycles unfold on timescales that span multiple human lifetimes. Each of these dates represents more than curiosity or spectacle. They are reminders that we inhabit a living laboratory in constant motion, always offering new puzzles to solve. The convergence we're witnessing now, solar wind battering Earth, an interstellar comet vanishing behind the Sun, earthquakes rumbling through the Pacific, demonstrate how even in an era of unprecedented astronomical capability, mysteries remain and patterns emerge that challenge our understanding of cause and connection. When 3II Atlas reappears or doesn't, when the data finally arrives and mission scientists analyze brightness curves, fragment counts, and spectral signatures, we'll learn something fundamental about how objects formed in alien star systems behave when exposed to our sun's radiation. The answer might confirm expectations or overturn them entirely, but either way, it adds one more piece to the cosmic puzzle we're assembling, one observation, one comet, one convergence at a time. The sky calendar stays open, the list of appointments grows longer, and for anyone willing to look up, the story continues unfolding overhead every single night.